Hi everyone, welcome back to Data Cadence. My name is Rahul and I work as a senior applied research scientist. And this is the part 2 of the video, choosing the best machine learning algorithm. We already have a part 1, so in case you haven't checked that out, just go and check that particular part because that's where we discuss why we are doing this and why this is a very important interview question and what is the importance of this in a day-to-day workflow as a data scientist. So without further ado, let's begin to part 2. So essentially what we were looking at so far was a few of the factors that you would consider based on which you can decide which is the best machine learning algorithm for your particular use case. We are going to continue that particular list. So just to recap, in part 1, we had a look at 5 such factors that you might want to consider when you are to choose a particular machine learning algorithm. Those were fairly straightforward and basic ones. We'll talk about a few of the advanced ones in this particular setup. So let's start with the sixth one, that is handling high dimensionality. Now, when it comes to handling high dimensionality, I think the first thing that we need to understand is what do we mean by high dimensionality. So it's the ability of an algorithm to effectively manage data with a large number of features, and that's essentially what it is. When it comes to KNN, so KNN kind of struggles with high dimensional data because of the curse of dimensionality, and this high dimensional data is what we call as the curse of dimensionality in the machine learning field. And when it comes to logistic regression, it can handle high dimensional data well, particularly when we are using techniques like regularization. When it comes to naive bias, so naive bias can work well with high dimensionality as it assumes the independence between your features. That is one of the assumptions that naive bias makes. For SVM, it's pretty effective with high dimensional data, especially with linear kernels that we can use. For decision trees, it can also handle high dimensional data, but it may overfit without proper pruning. And that's what we have been discussing throughout, that if you train a decision tree which is too deep, it can be prone to overfitting. When it comes to random forest, it's relatively better at managing high dimensional data than single decision tree due to the feature averaging. For gradient boosted decision trees, also they can handle high dimensional data well, but they require tuning to prevent overfitting. And for neural networks, they are capable of handling high dimensional data, but they may require careful architecture design in order to avoid the overfitting. And that's what we saw in most of the architectures above. The next factor when it comes to the choice of your model is the robustness to outliers. So robustness to outliers refers to the algorithm's ability to maintain performance despite the presence of anomalous data points. And we already have a very in-depth video and a very exhaustive list of things that you can try out whenever you have detected outliers in your data and what are some of the ways in which you can handle. So tap the video in the I button to go and watch that particular video. That's again a very exhaustive video where we talk about numerous approaches to handling outliers in your data. So coming back to this particular thing, so when it comes to KNN, it is sensitive to outliers as they can affect the distance computation that we do in KNN. For logistic regression, it is again sensitive to outliers, but the mitigation can be done with regularization. So the effect of outliers can be mitigated with proper regularization in your algorithm. When it comes to naive bias, it's generally robust because it relies on the probability. So that's there. For SVM, it can again be sensitive to outliers, but techniques like soft margin SVMs can improve robustness to a certain degree. When it comes to decision trees, they are also sensitive to outliers, but again, they can be pruned to reduce the impact of these particular outliers. For random forest, the robustness to outliers is slightly more compared to a single decision tree because at the end we are doing aggregation. And in case of classification, you can do majority voting to do the aggregation. In case of regression, you can do a mean or median based aggregation of your multiple decision tree outputs. When it comes to GVDTs, it also can be sensitive to outliers as boosting may focus too much on the difficult examples, and that's one of the things that we need to be careful about. When it comes to neural nets, again, neural nets are also sensitive to outliers, though techniques like using certain robust loss functions can help in case of neural networks. The next factor to decide is the ease of use and implementation. Now, ease of use refers to how straightforward it is to implement and tune an algorithm. And most of these algorithms are very well implemented in standard packages like scikit-learn. But it's often important to also understand that apart from implementation, also you have to tune certain hyperparameters, and that's where we'll talk about each one of these. So when it comes to KNN, it's pretty easy to implement with minimal parameter tuning. So packages like sklearn do a fairly good implementation of KNN and you can utilize those. Same thing for logistic regression and naive bias. So both are simple to implement and have well established libraries like sklearn to take care of the heavy lifting. When it comes to SVM, The implementation is slightly more complex due to the need to choose the appropriate kernels and the hyperparameters. And the implementation of SVM in sklearn is fairly good, but there is another library called libsvm that we can try out whenever we are looking at SVM, because that has a few more details and slightly better implementation than scikit-learn for SVMs. When it comes to decision trees and random forests, so again, libraries like scikit-learn simplify the implementation to a great detail. And again, GPTTs also, you do have libraries like XGBoost, CatBoost and LightGBM that can take care of all the heavy lifting, and it makes it a cakewalk to just implement all of these algorithms in a day-to-day workflow. When it comes to neural networks, it could be highly complex, requiring expertise in architecture design and hyperparameter tuning. But from an implementation standpoint, high-level APIs like Keras still take care of a lot of the heavy lifting, and it's fairly straightforward to implement a neural network in Keras. But yes, there could be many of the hyperparameters that you might need to tune, and that could be slightly challenging in case of neural nets. The next factor is the handling of imbalanced data. So handling imbalanced data refers to an algorithm's ability to perform well when the distribution of classes is not equal. And again, imbalanced data is something which is pretty common in a realistic setting. So let's have a look at how we can handle that. So KNN usually struggles with imbalanced data unless weighted voting is used. And we can use other techniques like synthetic data generation using algorithm like SMOT, but that is a topic for another video maybe. But yes, KNN in general struggles with imbalanced data unless we use some other mechanism to take care of that. When it comes to logistic regression, it can be effective with imbalanced data, but again, we need to do the appropriate class weighting in order to make it work with imbalanced data. And it also depends on the degree of imbalanced data. If it's an extreme imbalance, then again, there are other techniques to take care of that. But again, like I mentioned, that itself would be the topic for another video. When we talk about naive bias, so naive bias can handle imbalanced data fairly well due to the probabilistic nature of the algorithm. When it comes to decision trees, they can also handle imbalanced data, particularly when we are using techniques like class weighting, and that's what we saw for most of the other algorithms as well. For random forest, it's more robust compared to a single decision tree, especially when using balanced class weights or we are employing some sort of stratified sampling. When it comes to GBDTs, they are also effective, especially when techniques like boosting with resampling or class weighting are used. And in neural networks also, they can effectively handle imbalanced data, but they may also require careful tuning of the loss function, such as using a focal loss or adjusting the class weights. So like we saw, for most of these cases, using class weights or some of the other form of techniques to tackle the imbalanced data is fairly straightforward. And once you do that, a lot of these algorithms can take care of the imbalanced data, right? Let's talk about the next point, that is handling of the missing data. So handling missing data refers to an algorithm's ability to deal with datasets that have missing values without compromising on the performance. And when it comes to KNN, so KNN can handle the missing data via imputation, but the performance may be effective if there are many of the missing values in your dataset. When it comes to logistic regression, it cannot natively handle the missing values because it typically requires imputation or deletion of your missing data. Naive bias can also handle missing data by ignoring the missing feature during the probability calculation, but this might reduce the accuracy. SVM again cannot inherently handle the missing data. It does require imputation or deletion of your particular missing data. For decision trees, they can natively handle by using something known to us as surrogate splits, or making the decisions based on the available features and ignoring the features that are missing. And when it comes to random forest, so this can handle more effectively than a single decision tree, as it can use different subsets of features across different trees. And for GBDTs also, they can handle the missing data by allowing split on missing values or using surrogate splits. And the idea behind surrogate splits is to handle the missing values by providing secondary splits based on the other features. And neural networks also cannot handle the missing data natively. They also require some sort of imputation or deletion of the missing data. Let's talk about the last factor. I know this has been a long video, and that's the reason behind breaking it into two parts, but we have been as exhaustive as possible in covering all of these factors. So handling of non-linear relationships. So the ability of an algorithm to model and capture complex and non-linear relationships between the features and your target variable. When it comes to KNN, it is very much capable of capturing the non-linear relationships, though the performance may degrade as we have more and more high dimensions in the data or more number of features in our data. For logistic regression, it is limited to linear relationships unless we explicitly do or use some sort of polynomial features or do some sort of feature interactions on different features based on some sort of manual creation, or some sort of feature engineering is still required when you want to use logistic regression and make it work with non-linear relationships. When it comes to naive bias, so as it assumes feature independence, it may not capture the complex non-linear relationships very well. SVMs are very much effective when it comes to using non-linear kernels like RBF kernel that can very well capture the non-linear relationship between your features and your target variable. For decision tree, they can naturally capture the non-linear relationships via a hierarchical decision making. That's how the decision trees work. And follow up to that, random forest can also capture non-linear relationships, but more effectively than a single decision tree because they are averaging the output over multiple trees. For GBDTs, they are highly effective by sequentially correcting the errors in the priorities, so they can also capture the non-linear relationships very well. For neural networks also, neural networks out of all the above are extremely powerful at capturing the non-linear relationships. Especially deep neural networks with multiple hidden layers are really good at capturing the non-linear relationships, and that is one of the reasons that neural networks are also known as universal function approximators. So we have looked at a lot of factors when considering a different machine learning algorithms. So to wrap up, we have journeyed through the intricacies of several fundamental machine learning algorithms, analyzing them through the lens of key factors like training time, runtime latency, interpretability, and a lot more. And understanding these nuances isn't just about knowing which algorithm to choose, it's more about demonstrating your depth of knowledge and the ability to make informed decisions based on the specific needs of your project or the problem that you are trying to solve. By mastering these concepts, you are not only equipping yourself to excel in interviews but also strengthening your day to day work in data science. This comprehensive understanding is what sets you apart as a data science candidate, enabling you to make strategic choices that optimize the performance, enhance the interpretability of your data, and address the real world challenges effectively. So, if you found this deep dive useful, remember to like and subscribe to this channel for more such content that helps you sharpen your data science skills and prepare for success in your particular data science career. And I hope that this particular video helped you gain something new and it added a new perspective. So, I will see you in the next video then. Until then, take care, stay safe, and keep learning.